Hello everybody, my name is George Antonopoulos and I am a dental technician from the National Technological University of Athens. I am specialized too, in microdental and micro-orthodontic designing and analyzing, and today I proudly present you, on behalf of Dr. Takis Kanarelis, the famous orthodontist and elected president of ESLO 2014 to 2016, a brief summary of the study, Simulation in Orthodontics. The study was posted in the 11th Congress of ESLO, European Society of Lingual Orthodontics, that took place at Como of Italy, 5th to 7th of June of 2014. Abstract: Simulation in Orthodontics. The study is a theoretical approach to a digital microscopic analysis, on which the simulation on mechanical properties evaluates the way in which a retaining mechanism of the back of an orthodontic bracket develops stresses that tend to deform or cause breakage during the process of deboning it from the surface of a tooth. When one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction to that of the first body. In other words, the Newton's third law of motion: for every action, there is an equal and opposite reaction. Through digital technology, a 3D detailed model drawing was designed, edited, visualized and simulated by using high-level mathematics and finite element analysis method, FEA. 3 metal alloys took place in that evaluation: the 2205 stainless steel alloy, EN 1.4462, the Romanian Star CL, by Dentorum, and the MP1, by EOS GmbH. Appropriate design factors are based on several considerations, such as the accuracy of predictions on the imposed loads, strength, wear estimates, and the environmental effects to which the product will be exposed in service. What are all those considerations? Is a static nodal stress von Mises analysis, or a static displacement analysis, capable to specify standards in designing and constructing a perfect functional element? The conclusion is only one: using digital procedure and studying those parameters, it might be explained and eliminated all the opposite effect caused by an inadequate construction. In April of 1983, the Space Shuttle Challenger was one of NASA's greatest triumphs. It was the second shuttle to reach space. It successfully completed 9 milestone missions. But Challenger was also NASA's darkest tragedy. On its 10th launch, on 28th of January of 1986, the shuttle exploded 73 seconds after liftoff, killing the 7 crew members. The accident changed the space program forever. What was the problem that caused this fatal accident? Did NASA predict that possibility? And if so, how happened and 7 astronauts died? Is it possible to predict a design load? A material strength? The success of the functionality of a structure, no matter how small or big it might be? Through the years and following the technological progress, physics and mathematics, a very strong mechanical value was developed, FOS, factor of safety. It's a mechanical term, describing the structural capacity of a system, beyond the expected loads or actual loads. Buildings commonly use a factor of safety of 2.0, for each structural member. The value for buildings is relatively low because the loads are well understood and most structures are redundant. Pressure vessels use 3.5 to 4.0, automobiles use 3.0, and aircraft and spacecraft use 1.2 to 3.0, depending on the application and materials. But, what about in our medical field? Can we predict the loads, and the mechanical strength of an orthodontic appliance, or a part of it? Big or small? Simple or complex? And what are the benefits of a study like that in our clinic procedure? Might we have a designing prognosis before any structuring method is completed? Somewhat so. We were trapped between the micro-world and the macro-world, separating them entirely the one from the another. In fact, The only thing that differs is the size into the space and the time, and the universe created his creatures to have a specific structure. In order to examine further the concept of creation, we conclude that the laws that govern everything in the universe, for both the micro-world and the macro-world, are no different. The language that we are using on the basis of these two worlds are the mathematics. In 2001, the well-known researchers in the field of orthodontics, William A. Brantley and Theodore Eliades, with the magnificent literature, Orthodontic Materials, Scientific and Clinical Aspects theme, page 114, present the in vitro tensile bond strengths of direct bonding orthodontic adhesives to a metal bracket. They indicate that spot welds and broken mesh on the base of a bracket could cause high stress concentration in an adhesive. So what we did? We designed, analyzed and simulated these micro-adhesive mechanisms theoretically, which we all know about their function on the base of an orthodontic bracket. From the ancient times, with the Archimedes palimpsest, and the algebraic description of the sphere, to the powerful modern designing softwares, we even calculate their volume, surface area and why not their bonding area. For each one of those micro-mechanisms and during the debonding of an orthodontic bracket from the surface of the tooth, using the third law of Newton, the well-known of action and reaction, and with the help of finite element analysis we studied the elastic regions, the displacement, the von Mises yield criterion and the possibility of a damage or a cracking on them. We applied physical and mathematical laws, elastic constants and material properties, of the three well-known materials, 2205 stainless steel alloy, EN 1.4462, the Romanium star Cl, of Dentorum, and the MP1, of EOS GmbH. We note that all these values are official, concerning structuring procedures, and were given to us by the medical application and mechanical department of each company. One of the most important information was the FOS value, factor of safety. We finally understand that under a pressure of 13 megapascal our design withstands approximately 3 times our experimentation load. After all, we had a prognosis of their functionality. The final results of our study. Unfortunately, when we apply over 500,000 equations polynomials, on such small surfaces, of a few square microns, it's too difficult to analyze in a few minutes, the process and the results. The final conclusion is that, with the help of high-level mathematical approaches, and the means of a software sufficiently developed on the scientific foundations of mechanical and other properties of materials, the simulation procedure will give to the orthodontic technology the required support, in order to be able to develop more secure designs, most correct studies, and better construction results of orthodontic appliances, with a view to improving health, in the positive development of the human race. You might download a short video of this presentation and the references of our study, through our posted QR codes. Coming soon, with new studies, designs and manufacturing. Thank you for your time. George Antonopoulos. June of 2014. Simulation in Orthodontics.